All right, ladies and gentlemen, Mr. Dorfler here. Starting a new approach to notes. We're just going to see how this chapter goes. We're always trying to make it better for everybody. And so we're going to start off chapter 12, which is, again, looking at forces, but we're going to be looking at the individual who really, popularized it, Sir Isaac Newton. Okay, we're going to be looking at Newton's laws as we go throughout this chapter and how we can calculate certain physical situations and determine how they fit with Newton's laws. Okay, so starting off right from the get-go here, Newton's first law. Okay, Newton's first law states that an object at rest remains at rest and an object in motion maintains its velocity, meaning an object in motion maintains its motion unless it experiences a net force. So an external force needs to happen upon the object, whether it remain at rest or if it's currently in motion, for it to alter its current motion status. Okay. It describes what happens when no net force is acting on an object. Okay. It just continues doing what it's doing. When we have that net force applied, that's when you're going to notice a change in the state of motion. If we look at a sliding book, when we try to slide a book on carpet, if we just give it a shove, it's eventually going to come to rest, probably in a fairly quick amount of time, because the friction between the carpet and the book is going to eventually overcome the force that was involved there. So the book is going to stop. However, if there was no friction present, then that would mean there would be no net force exerted on the book, and that book would continue to move in the same direction at the same velocity. Okay. You also might notice that the slides that you are seeing on my screen or on your screen now have words that are in red. Okay. Those are the words that need to fill in the blanks of your copy of the notes. That way you're maintaining an open ear as we're going through here, and also you are writing down some important information as we proceed. All right. So again, Newton's first law. Let's look at the motion of objects. Unless acted upon by a force, an object in motion will continue moving in that same direction. How about this? An infinitely long and frictionless bowling alley. Now again, those two ideas, infinitely long and frictionless, really are never going to happen in the real world. Okay. Nothing can really be infinitely long that is feasible. And frictionless, there is friction no matter how small amount of friction is present, there is still friction. Okay. Even when an object is falling, you have air resistance. That is a form of friction. Okay. Anyway, a ball rolled in a straight line down this alley will keep rolling and rolling and rolling until a force is acted upon that, which typically a force would be friction, or, if you got to the end of the lane, would be the bowling pins. Okay. But in reality, like I said, not going to happen because we have so many other factors that are occurring. Again, frictionless. Not only you're talking about having no friction between the ball and the flooring it's rolling on, but also that wind resistance I mentioned. Okay. When an object is rolling, is also going to incur some wind resistance. Like when you're driving a car, okay, you're going to encounter wind resistance in conjunction with the friction provided between the tires and the road. It's just not going to happen. And this whole idea about objects moving gives us what's called inertia. And really, Newton's first law is often called the law of inertia. What is inertia? Well, it's the tendency of an object to resist a change in motion. That is, unless an outside force acts upon it. So, inertia says an object at rest will remain at rest. A moving object continues to move at a constant velocity. But there are certain factors that play a role in the concept of inertia. One of them being mass. An object whose mass is small is going to have less inertia and takes less force to accelerate, like a sports car. Okay, oftentimes sports cars have lower mass, and that way they can have these really powerful engines and maintain and get up to some really high speeds. An object whose mass is large has more inertia. Okay, it takes more force to accelerate. Look at like a semi truck. Okay, big piece of equipment here. It takes a lot of force to get that thing moving. Okay, whereas with a small sports car, it takes a lot less force to get that car moving. And also when it comes to stopping, it takes a lot less force to get the sports car to stop than it does to keep the big semi truck to stop. Again, because once that semi truck gets going, it has inertia and does not want to stop its current state of motion. So it's going to have a lot of braking power required in order to slow it down and come to a stop. Another example we see is sliding in the seat of a car that is turning sharply. Okay, if you've ever been in a vehicle, say you're leaving the interstate and you're on an exit ramp, okay, and a lot of times exit ramps have curves on them. If you're going fast, like you are on the interstate, but not breaking the speed law, right? You're going to notice that when you turn, you tend to continue moving either left or right, depending on what direction the car is going and what direction the car is being turned. If you take a turn to the right, you're going to find that your body goes to the left, because that is why you are experiencing inertia. As you are in the car, you have inertia. You have a tendency to continue going in a straight line when you're in the car. And when you turn, your body wants to continue going on that straight line, but the car does not, because of its contact with the road and tires that provide enough friction to have the car turn, but you want to keep going in that straight line. Backwards facing car seats. Okay? For quite a few years now, there's been a really big push to make sure that every child up to a certain size and age continue to sit in a seat that faces backwards. Because if you think about if you come to a really sudden stop, okay, even when you're older, you tend to have your head move like that, your back jerk like that, okay? That can cause severe damage to your bones and your muscles and even possibly your brain. And so that's because that seatbelt that's over you, it's only applying a certain level of protection, if you will, to your body. And so a lot of your force goes that way. But the backwards facing car seats for babies, if you were to stop suddenly going forward and the child is facing backwards, all of that force will then be spread around the entire body and the seat, reducing the sharp movements placed upon the infant's body. So that's why you see so many laws requiring infants and even toddlers sometimes to face backwards in the car seat, as long as it's properly fastened in there. I want to show you this video later, actually. I'm going to put that link into the link for this. That way you can watch it on your own. It's only about 5 minutes at most, I believe. It's an interesting video regarding the idea of physics and Newton's laws in conjunction with sports or anything that involves the type of motions like football does. Okay. Moving on to Newton's second law. Newton's second law states that an unbalanced force acting on an object will equal the object's mass times acceleration. And Newton's second law describes the effect of an unbalanced force on the motion of an object. And we can calculate Newton's second law by the formula F equals m times a, or force is equal to mass times acceleration. The unbalanced force, which is the capital F in the formula on an object, is going to determine how much an object speeds up or slows down. So typically, if the force value is small, okay, you're putting a small amount of force on there, you're only going to get a small movement typically, okay? But again, it's all situational. Now, let's break down the formula, okay? Again, the capital F, the variable capital F in the formula is the force, and we measure force in newtons. Now, we can convert between newtons and pounds if we ever wanted to, because a lot of times in physics books or in science books, you might actually see the weight of an object in the unit of newtons. And so, we don't typically in our everyday lives use newtons when we talk about weight of objects, but we could convert it if we need to, okay? So obviously it takes about 4.5 or so newtons to equal 1 pound. But anyway, anytime we calculate force, it will be in newtons. That is our unit. Okay, I'm a stickler with units if you haven't figured it out yet. And that is capital N. So when you calculate force, you would calculate the value or the magnitude. So, and then you label it with the capital N. The M in the equation is mass, and we measure this in kilograms. Again, it must be in kilograms for us to calculate force. So there may be times where we would have to convert from another unit into kilograms, but we must have kilograms. The mass of the object will affect both the acceleration and the force being exerted on an object. So again, these are very big players when just determining the force and acceleration of an object. And lastly, the third part, the A in the formula, acceleration. Again, acceleration should not be anything new to us. Its units are meters per second squared. And so the amount of force applied to a moving object will affect the acceleration of that object. Now, just like what we saw in the last chapter, anytime we are dealing with a formula, we can and will rearrange the formula to solve for any of the unknown variables. We could rearrange it to solve for mass or acceleration. So it is very important that you know the units for each variable. So how do we solve Newton's second law problem? Okay, first of all, write down the formula. Get in the habit of writing the formula down. F equals m times a. I call that my general formula. Anytime we get the basic formula in there, that's our general formula. Determine the known values of the problem and include the units. Then you will identify any unknown value or variable in the problem and include the units as well. Once you have determined the known and unknown values in the problem, you then insert them into the formula for force. Now, you can do this one of two ways. If we have to solve for anything else like mass or acceleration, if you are the one type of people like myself who prefer to rearrange the formula first, by all means. Or you can just simply plug them in and rearrange them as necessary. But since we're solving for force, generally, we don't have to do any rearranging. Once we've inserted the known values, solve it mathematically. And again, force is in newtons, capital N, mass is in kilograms, A, acceleration is in meters per second squared. So let's go ahead and solve this problem here. I'm going to actually fix the camera here. And while you are reading the problem, I am going to get myself a calculator. I did not come prepared for this. All right, so we have a zookeeper, and they're going to lift a stretcher that holds a sedated lion. The total mass of the lion and stretcher is 175 kilograms. Now, it's important to note that we do include the mass of the stretcher with the lion because both objects have to be lifted up. And the upward acceleration of the lion and stretcher is 0.657 meters per second squared. What force is needed to produce this acceleration of the lion and the stretcher? Well, let's go ahead and get to my camera so hopefully you can see it. All right. So going and following those steps that we saw on the previous slide. All right. Pardon me as I kind of adjust this here. It's a little close for me. Again, force is equal to mass times acceleration. Okay. Next, we're going to write down what we know. Okay. We know that the mass of the lion and the stretcher is 175 kilograms. Now, again, kilograms is the appropriate unit. We don't have to do any converting from this number. And we see that our upward I don't know why I did that. Our upward acceleration is 0.657 meters per second squared. And we are trying to figure out what our force is. Again, newtons. Put our unknown with units listed there. So since we are solving for force, I don't have to rearrange anything in the formula. So I'm just going to put force is equal to our mass, which is 175 kilograms, multiplied by our upward acceleration of 0.657 meters per second squared. And so once I've got that set up, I put those into our calculator. 175 multiplied by 0.657. And we get an answer of 114.975 newtons. However, we have a thing called significant figures in science class, and we really need to try and adhere to them. And I know we really haven't talked about them just yet, but we have to look at the numbers that we calculated to determine our lowest number of sig figs, okay? In this first one, we have 1, 2, 3 significant figures. In the second one, we have 1, 2, 3 significant figures. You might be asking yourself, well, why is that 0 not considered significant? Well, zeros are kind of an odd bunch when it comes to determining what is significant in terms of values. And there's quite a handful of rules that we have to abide by. The rule that we're going to look at here is we have this 0 that is to the left of the first significant figure, which is 6. And that means any zeros to the left of the first significant figures are not considered significant themselves. So that means we have 3 significant figures here, 3 significant figures here. So my final answer after I do some rounding, again, that's not a very good looking 9, is I'm going to round this number that I calculated so that it fits the significant figures. It reports in 3 significant figures. And I think the best would be just to round the 9 up, and I'll have an answer of 115 newtons. Okay? Again, don't worry too much about significant figures at the moment. Okay? We have switched some things around, so we haven't quite talked about them yet, but we will. So just preparing you for that. And that wraps up the video for section 1. Sorry, I'm upside down, and there we go. So that wraps it up. If you have any questions, by all means, bring them to class, and we will address them. Otherwise, make sure to fill this out. If you need any copies of the PowerPoint, I have all the completed sets. Otherwise, you can feel free to print them out yourself. All righty. So I will see you all later. Most of you I'll see in class. Bye-bye.